Alright. So I have not been here for a while because school has started, so you're going to be seeing a lot of less frequent uploads, but that's not what I'm here to talk about. I want to talk about what are cupolae and rotundae. So if you don't know, cupolae and rotundae are types of polyhedra, mainly Johnson solids. So what are they and what different things can you make out of them? So let's say you take a n-gon. You could take any n-gon, any gon with any number of sides, but the main ones are usually considered polyhedra. Use equilateral triangles, squares, and regular pentagons. So no weird shapes, and it's usually just triangles, squares, and pentagons. So you choose your n-gon. Let's say you choose a pentagon, and you take a hengon, which is a 10-sided shape, and you take your hengon, and you put that at the bottom. So you're gonna use a 2 n-gon, if that makes sense, 2 times the sides. And you want to make an alternating band of squares and then triangles, and square and then triangle, square, triangle, all the way around until you meet up with your original one. So you have like a pattern: square, triangle, square, triangle, square, triangle. So you do that, and then what you want to do is close all of them up, so the top vertexes of 2 neighboring ones will end on top of each other. A better way to explain it is if you were to take like magnets or like paper, cardboard, or whatever, stick it all together so you have your alternating band, and you let it all collapse into the center. And in this case, that would be the perfect hole for pentagon. That makes sense because the triangles go in, but they're just a single point. So the 5 triangles for the 5 vertexes, squares, sides of the pentagon, so you can stick a pentagon right there, and that's how you make a pentagonal cupola. C-U-P-L-O-A, yeah, cupola. I'm sorry if I spelled that wrong. But what about a rotunda? A rotunda, spelled RONTUNDA, is, you can only really do this with a pentagon. So you take your pentagon, and instead of an alternating band of squares and triangles, you're using pentagons and triangles. So it's only that difference. Once you stick it up there, you get a pentagonal rotunda instead of a pentagonal cupola. But what can you do with rotundas and cupolas? Well, you can do things like combine 2 of them, and there are 2 different types of combinations. Let's say you want to stick a triangle. Let's say you take one cupola, let's say a triangular cupola, and you stick it to another triangular cupola, and their bases meet. So you could like get rid of those bases, those 2 n-gons, and then put those together. There are 2 types of ways of putting those together. If you put triangle to triangle, square to square, then you'd get a gyro. So a gyro by cupola. So this would be a triangular gyro by cupola. Say it with me. triangular gyrobicupola. It's a mouthful, but once you get into the polyhedra community, it is not that hard to say. It's one of the easier things to say. But what if you try to stick triangle to square and square to triangle? What would you get then? It would be, let me see if I can remember. Ortho. You did the ortho. Sorry, I took so long. Awkward pause there, but you got ortho. Triangular orthobicupola. Gyrobicupola, orthobicupola. Gyrobicupola, orthobicupola. There's a difference. Gyro, G-Y-R-O. Ortho, O-R-T-H-R-O. No, O-R-T-H-O. Ortho. Simple. But what if you try to combine a pentagonal cupola and a pentagonal rotunda? And yes, you do use a prefix of pentagonal because I don't know why it just works like that. But let's say you stick triangle to pentagon and pentagon to triangle. What do you get then? It's not a gyrobicupola. It's not a bicupola, but it's not a birotunda either. It's a cupula rotunda. You say cup and then you say cupula and then rotunda. Cupula rotunda. CUPLOROTunda. Cupula rotunda. So you can either have a pentagonal cupula rotunda or a pentagonal orthocupula rotunda. Makes sense, right? But there are other things that you can do. Now imagine you take a truncated dodecahedron. If you don't know what truncating is, imagine cutting off the vertexes, corners of a dodecahedron. So you get a truncated dodecahedron. The pentagons become hengons, hengons, and the vertexes become triangles. Makes sense. But what if you try to do something? Well, there might be a new concept to you about augmenting. Augmenting basically means, okay, let's start with, what should I start with? A triangular prism a prism. What's a triangular prism for simpler context? Now you have a square. You have a square in this prism. You replace it with a pyramid, a square pyramid. That is an augmented triangular prism. If you try to do a bi-augmented truncated prism, then you just get copointer sides, so it's still a polyhedra, just not a strictly convex. It's not a strictly convex deltahedra, but it is a polyhedron. But that's a side tangent. So you have augmentation. But what if you try to augment a truncated dodecahedron? What would you get then? Well, you see the base of that. Remember the base of that rotunda, cupola? Remember the base of the cupola, the pentagonal cupola? What you see is a hengon, right? But what else you see on the truncated dodecahedron? You also see hengons. So you can attach that on, you can put that on, and you get an augmented truncated dodecahedron. Now when you're reading polyhedron like this, you don't read it from right to left. If you want to know how to construct it, you read it from left to right. Right to left, not left to right. But you start with it. So in augmented truncated dodecahedron is different than truncated and augmented dodecahedron. Well, actually, no, it's not because no, it's not. But you start with the dodecahedron, you truncate it, and then you augment it, and you get you get an augmented truncated dodecahedron. So that is basically what cupola and rotunda, or cupolae and rotundae are. But yeah.